Today in class we're going to talk about binary trees. So remember when we looked at linked lists, linked lists were sets of objects that each contained a little bit of data, right? And some link to another object of the same type, right? And these instances of these objects were all linked together in a list, hence the name, a linked list, right? And they were linked together until you got to a pointer where to one of these instances where the next pointer is null, right? So we called the beginning of this list the head, and that's usually the object we kept track of. And then sometimes we would keep track of the tail, right, which is the very end of the linked list. So linked lists, like I said, contain some data and then contain up to one other node, right? So here the head points to this guy, and he only points to something else, and she might point to that, and so on. But what if, right, so the linked list ends when you get to a null pointer. But what if instead we had two next pointers? So from this guy, we wanted to point to this element and this other element, right? So he has a next and a next two. And same thing with this guy. He points to a next and a next two. This guy points to a next and next two. So instead of having a single list now, it's sort of like a tree, right? It starts branching off from each other. So that brings us to the next sort of evolution of this concept, and that's binary trees. So binary trees, just like linked list nodes, contain some data, but now they have a link to up to two other nodes, right? So here's the beginning of our tree, and he has a link to a left piece of data and a right piece of data. And those each have a link to either the left or the right, right? And a binary tree, right? Before we were only traversing in one order. Now if we're traversing down the tree, right? You reach the end when you've found one of those null pointers, right? And we call these nodes that have pointers to null, to only pointers to null, we call them leaves, right? So again, taking this analogy of a tree, right? Trees have branches, right? They branch off, and they have leaves when you get to the very end of a branch. In the same way, we're not going to call this a head anymore. We're going to call it the root, right? It's the base of the tree, right? So we have a leaf, we have our root, we have branches. And this is where the analogy sort of falls apart because internal nodes, right, are the nodes that are inside of the tree. So they're not the root, they're not the leaves. They have some, something points to them, right? A root doesn't have anything pointing to it. An internal node has something pointing to it, and it points to something else. Right? So internal nodes have at least one child. They could have two. So that brings us to a little bit of terminology about trees, right? So we've already discussed a little bit, right? The root, the leaves, the internal nodes. When we say paths diverge, that means they're branching, right? So, branching. So if you watched this video previously, I actually did make a little bit of a mistake here. So I'm re-recording the second half of this video to correct for that. So the mistake was with how we calculate the height, and it affected sort of all of the slides from here out. But if you're watching it for the first time, you can just follow what we're saying, and everything is now correct. So there's a couple pieces of terminology that we use with binary trees that will help us as we describe them. So the first are a set of values that we can extract from the tree. Numerical values tell us something about the size of them in different ways. So the first thing is the node depth. So the depth of a particular node is how many links between the root and the node that we're looking at. So if we're talking about the root itself, the depth of the root is 0, right? Because there are no links between, the number of links between the root and itself is 0. Right? You're right there. Whereas the depth of this angry face down here is 1, 2 links. So its depth is 2. Right? And we say that the level, right? So going back to this last term, the level is a set of nodes with the same depth. So here, level 1 is the set of the happy and sad face. So that's the set of nodes at level 1. So here's where I made a mistake before, and that was in calculating the height. So the height is actually the maximum depth of any node in the tree. So here, this guy's depth is 0, 1 and 1, 2, 2, 2, 2. And there's nothing at level 3. There's nothing with depth of 3. So the height here of this tree is 2. Right? So there is some discrepancy. If you look on the internet, some people would describe this as being a tree of height 3 because there are 3 levels, 0, 1, and 2. But to keep consistent with the Zai book, we're gonna use the calculation here that the height of this tree is 2, right? Because it's 2 sets of nodes to get to any, from the root to any node. Sorry, 2 edges to get from the root to any node, right? So that brings us to, so those were the terminology bits on sort of full calculations, numerical calculations on a tree. And then we have sort of 3 sets of descriptors as well. So the first one is whether or not a tree is full. So a tree is full if each node has exactly 0 or 2 children. So here we can see that this node has 2 children, 2 children, 2 children, and these all have 0, 0, 0, and 0 children. So this tree as it is full, right? A complete tree is one where all of the levels have the maximum number of nodes. So there's 2 to the level nodes in each level. So here, level 0 has 1 node, the root. Level 1 has 2 nodes, 2 to the 1, 2 to the 0 equals 1, 2 to the 1 equals 2, and 2 to the 2 equals 4. So we can see that this tree has all 4 nodes in this last level, all 2 nodes in this second level, and it has a root. So it is complete. And then a perfect tree. So this is again where the discrepancy in the way we calculate height in the last version of this video. A perfect tree is both full and complete, and all of its nodes are in that last level. So it has exactly 2 to the height of the tree leaf nodes. So here the height of this tree was 2. So we need 2 to the 2 leaf nodes, and they all need to be in level height, right? They all need to be at level 2. And in this particular example, that's true, right? There's 1, 2, 3, 4 leaf nodes, and they're all at level 2. So in this case, we saw that it was already full, right? We saw that it was complete, and we saw that it's perfect. Oh, right. So what if we add this set of nodes to our tree, right? Well, is it still full? Well, every node has 2 or 0 children. So yeah, it's full. Is it complete? So all the levels have the maximum number of nodes, except possibly the last level. And the nodes in the last level are all the way to the left, which they seem to be, right? In that case, it is complete. And then for it to be perfect, it has to be both full and complete, which it is, and it has to have 2 to the height leaf nodes. So here, height is 2 to the 3, right? 0, 1, 2, 3 levels. So the height's 3, and that's 8 leaves. Does it have 8 leaves? No, it doesn't have 8 leaves. So it's not perfect. It is full and complete, but it's not perfect. What if we now only added these 2 nodes? Right? So the first question, is it full? Well, 2 children, 2 children, 2 children, 2 children, 0, 0, 0, 0, 0. So yeah, it's full. Is it complete? Well, all levels have to have the maximum number of nodes, except possibly the last, which is true. The last level doesn't have all the nodes. And in the last level, all the nodes are to the left. Well, that's no longer true, right? Because these nodes are not all the way to the left. So it's not complete. And can it be perfect if it's not complete? No. So it is full, but it's not complete and it's not perfect. Well, what about this guy? So now we have all these nodes on the left here, but this guy is missing his children. So is it full? 2, 2, 2, 2, 0, 0, 0, 0, 0. Yeah, it's full. Is it complete? No, because this level now doesn't have the maximum number of children. So it's not complete. And since it's not complete, it can't be perfect. So the question is about this last tree. Is it complete? No, it's not complete, right? Because this, again, like we said before, both of these levels are missing some nodes. So it's not complete, which means it can't be perfect. But the question is it full? Well, let's see. We have 2 children, 2 children, 2 children, 0, 0, 0, 0. But this guy only has 1. The root only has 1 child. So is it full? No, it's not full. Right? So then how do we implement trees? So we're actually going to go into implementing trees in class. And there's 2 ways to do it. So just like with linked lists, there were 2 ways to implement linked lists. One was using generics, right? Where you have some generic binary tree node and it contains some other class type, or using new node classes, right? Like we saw originally for linked lists. And that's what we're going to go through in class on Monday. So in class, we're going to go through a couple examples where we implement binary trees, and we're going to do that using new node classes. All right, well, I will see you all then.